A thorough understanding of pitch and power control can enhance flying precision and, more importantly, be a major factor in accident avoidance. Although this subject is well understood by most jet pilots, both civilian and military, lack of understanding by pilots of light airplanes has made this a controversial area for decades. In this video, we will examine the power fixed, power variable rule, use computer simulation to show why the rule was created, and clarify how it is applied in common flight situations. At the end, we will see how proper use of flight controls can save both your life and your airplane. Any explanation of pitch and power control must be based on solid aerodynamic principles and also answer a number of questions. For example, if flight path can be controlled with pitch or power, why would one method be superior to the other? Or, what determines whether a situation is power fixed or power variable? Also, how do the regions of normal or reverse command affect pitch and power control? In addition, why are U.S. Navy fighter pilots taught to use a technique that is opposite to that used by U.S. Air Force or airline pilots? We must not only answer these questions, but also look at the issue of why so many light airplane pilots were and are being taught pitch and power control methods that are contrary to professional pilot procedures. Let's start with the first question. So, why would one method be superior to the other if flight path can be controlled with either pitch or power? The answer is responsiveness. Let's look at a computer simulation where flight path is changed by pitch and then compare the result when flight path is changed by power. We will use corrections that are about 3 times greater than normal to amplify the results. First, we will fly parallel to the glide slope with no changes. Next, we will correct toward the glide slope with pitch only. Now let's correct toward the glide slope with power only. Notice that the pitch-only correction intercepts the glide slope much sooner than the power-only correction. Let's repeat the corrections from above the glide slope. Again, we will fly parallel and above the glide slope. Now we will see a pitch-down correction only. This will be a power reduction only. Since we see the same result as from below the glide slope, it is only necessary to look at the above or below cases, but not both, since one is the mirror image of the other. To see why pitch corrections are so much faster than power, let's look at what makes a flight path change direction. To understand the differences between pitch and power corrections, we have to remember that both lift and drag for any particular airplane depend only on the combination of angle of attack and airspeed. So when thrust is added and the pitch attitude is maintained constant, lift will increase as the airspeed increases. As lift exceeds weight, there is an unbalanced force perpendicular to the direction of travel that over time will change the flight path direction. Adding thrust is not the fastest way to change the flight path, since it takes time for the airspeed to change, plus additional time for the engine to respond. However, pitch changes provide an immediate change in angle of attack that instantly provides a large short-term increase in lift with an associated significant change in flight path direction. Of course, if power remains constant, this initial sharp change in flight path will not be sustained as the airspeed changes. The bottom line here is that pitch changes flight path much faster than power. Now let's compare pitch and power corrections for airspeed control. Unlike the previous plot, this one compares airspeed change versus distance. The first plot shows the reference airspeed with no changes being made. Next, this plot shows the airspeed increase after a pitch down change was made. This plot shows the airspeed increase after a power change for a fast responding engine. Last, we see the airspeed increase after a slow responding engine has increased power. Notice that changing airspeed with pitch or a fast responding engine, typical of a light airplane, produces almost identical results. The slow responding engine, which models a typical turbojet, is only slightly slower. This picture shows the reasons behind the previous computer result. Any change in the thrust-drag relationship will cause the airspeed to begin changing. A rapid change in either thrust or drag will have the same effect. Since drag can be changed immediately by angle of attack changes, the only real difference in response time is due to the time for the engine to respond. Small reciprocating engines respond very quickly, so there is little response time difference compared to pitch changes. Turbojet engines may take several seconds to respond, which accounts for the slight difference in response time. Pitch changes flight path much faster than power, while pitch changes airspeed only slightly faster than power. Therefore, controlling flight path with pitch and airspeed with power provides great ability to precisely control flight path with only a slight reduction in airspeed responsiveness. Since catching airspeed deviations early and making thrust changes to reduce the error is more important than how long it takes for the error to be resolved, the small loss in airspeed response with power changes is not an issue. Precise flight path control is the most important quality. These control response results are the reason that all autopilots or flight director systems on any airplane control flight path with pitch. There are no airplanes that control flight path with autothrottle. There is another reason why flight path should be controlled with pitch and airspeed with power. There are some situations where using the opposite method will lead to incorrect responses. Consider the following cases. If we are high and fast, the correct response is to pitch down to intercept the desired flight path and throttle back to slow down. This is compatible with the pitch for flight path and power for airspeed rule. Attempting to apply the pitch for airspeed and power for flight path rule, reducing power to go down is okay, but pitching up to slow down results in a greater deviation from the desired flight path. In this case, pitching up to intercept the flight path and throttling back or maintaining the same power setting to slow down is compatible with the pitch for flight path rule. Attempting to apply the opposite rule by adding power to intercept the flight path can increase the airspeed further. In this high and slow case, the pitch for flight path rule is correct by calling for a pitch down to intercept the flight path and adding power or keeping it constant to increase the speed. The pitch for airspeed rule will increase the speed, but throttling back to intercept the flight path can further reduce the airspeed. The pitch for flight path rule dictates the obvious correct response, which is to pitch up to intercept the desired flight path, and power up to increase the airspeed. The pitch for airspeed rule says to pitch down to increase the airspeed, which leads to a larger flight path deviation. The pitch for airspeed rule only gives the correct pitch and power action when the airspeed is currently at the target value, while the pitch for flight path rule calls for the correct pitch and power action for all flight path and airspeed errors. Now that we have seen why flight path should be controlled with pitch, let's examine the second question. Before we can determine whether a situation is power fixed or power variable, we have to first state the power fixed power variable rule. If you are wondering about the many valid situations where airspeed is controlled with pitch, and feel that there may be a conflict with the discussion so far, don't worry. Everything will fall into place after we discuss the power fixed power variable rule. Lack of familiarity with the power fixed power variable rule is probably responsible for the controversy surrounding the control of pitch and power throughout general aviation. The power fixed power variable concept has been part of basic flight training in the U.S. Air Force for at least the last 55 years. The concept separates maneuvers into either power fixed or power variable situations. These pictures from Air Force Manual 51-37 show a power fixed situation on the left where pitch attitude is controlling airspeed. On the right is a power variable situation where pitch attitude is controlling rate of descent and power is controlling airspeed. The manual's text states that pitch attitude control is used primarily to maintain an altitude or to control the rate of climb or descent. Pitch attitude control may be used to control airspeed during maneuvers requiring a fixed power setting. Power control is used for maintaining or changing the airspeed, except for maneuvers using a fixed power setting. For example, full power for a prolonged climb. In the early 1970s, flight instructors could renew their certificates by attending a 3-day clinic taught by a team from the FAA Academy in Oklahoma City. During these clinics, the team taught the power fixed power variable concept, and this is one of the handouts provided. It states in part, there are only two basic power conditions for flight. They are, number 1, power is variable or adjustable, and number 2, power is fixed, by choice or by accident. When power is variable and available for the purpose of controlling speed, then power controls speed and elevator controls altitude or rate. Examples are, in level flight, power controls speed and elevator controls altitude. In rate climbs and descents, power controls speed and elevator controls vertical velocity. And during an ILS approach, power controls speed and elevator controls glide path. Unfortunately, the power fixed power variable concept never made it through the FAA bureaucracy from the FAA Academy to those who write the pilot instruction manuals, so it has never become a part of the general aviation knowledge base. We can formulate the Air Force and FAA concept into the power fixed power variable rule. It states that a situation is power variable when both flight path and airspeed are to be controlled precisely. In this case, we control flight path with pitch attitude and airspeed with power. A situation is power fixed when only flight path or airspeed is to be controlled precisely. In this case, we control either airspeed or flight path with pitch attitude. To clarify how the rule is applied, we must understand that occasional changes in power are just adjustments in the fixed power setting. This does not change the situation to a power variable condition unless you now desire to control both flight path and airspeed precisely. In other words, touching the throttle during a fixed power maneuver does not change it to power variable. The vast majority of flight situations are power fixed. Power variable situations are quite rare. Most misunderstandings regarding these rules come from attempting to apply the power variable rule to power fixed situations. The examples shown here may help to lift some of the confusion regarding the application of the power fixed power variable rule. The majority of any flight is power fixed. Climb is at a fixed power setting, where airspeed is controlled with pitch attitude. Cruise is a fixed power setting, where pitch attitude controls altitude. During a descent, where power is also fixed, pitch attitude controls the pilot's choice of either rate of descent or airspeed. The visual traffic pattern is also a source of confusion. A situation cannot be power variable without being able to precisely determine flight path, either electronically or visually. This means that the traffic pattern descent must be a power fixed situation until we are close enough to precisely determine our approach path visually. How close depends on pilot experience. So the visual traffic pattern descent begins as a power fixed maneuver, where pitch attitude is controlling airspeed. During this time, small power adjustments are simply changes in the fixed power setting. When close enough to determine the progress on our visual glide path, the situation can revert to a power variable situation, where glide path is controlled by pitch attitude and airspeed with power. For long runways, where we are satisfied with the flight path when the precise visual flight path comes into view, the approach may be continued as power fixed, with no power variable segment at all. This case is very common, with the precise control of visual glide path with pitch and airspeed with power reserved for landing on short runways, especially if obstacles are present. Precision ILS approaches in any airplane are flown with the power variable method, using pitch attitude to control glide slope and power to control airspeed. However, we will see in the following discussion on command regions that jets must use the full power variable rule during an ILS approach, but light airplanes operating in the region of normal command may use an easier power fixed method, where airspeed is allowed to vary slightly while small glide slope corrections are made with pitch attitude. Now is the time to look at the effects of command regions and answer question number 3. How do the regions of normal or reverse command affect pitch and power control? First, we have to define the command regions. The regions of normal and reverse command are traditionally defined by the minimum point on the drag versus airspeed curve. However, the flat part at the bottom of the curve has important characteristics also. Therefore, we will divide the drag curve into 3 regions. On the left, where drag increases strongly with decreasing airspeed, is the region of reverse command. In the center, where there is little change in drag with airspeed, we'll define this as the region of neutral command. Last, on the right, where drag increases strongly with increasing airspeed, we have the region of normal command. We will plot drag divided by weight instead of drag alone, so that we can compare vastly different size aircraft on the same screen. Drag curves are influenced by wing shape and the cleanliness of the aircraft design. Low aspect ratio wings, with their short and wide shape, produce a large drag at slow airspeeds. Clean airframes produce a slowly increasing drag curve with increasing speed. Therefore, light airplanes with high aspect ratios and relatively dirty airframes typically have very small regions of reverse command. Jet transports also have high aspect ratios, but very clean airframes, which produce a significant region of neutral command. Low aspect ratio jet fighters also have a large region of neutral command, but the additional low speed drag caused by a low aspect ratio increases the size of the region of reverse command. So, how do these command regions affect pitch and power control? To find out, let's look at some computer simulations. We will start with the region of normal command, where we have already seen how pitch responds compared to power. But we will now also see the effects of combining pitch and power together, as well as the corrections made while above the glide slope. First, the flight path with no corrections. A faster than normal plotting speed will be used. Next, the pitch-only correction followed by the power-only correction. Now we will combine pitch and power together so that airspeed remains constant after the pitch change. Notice that the flight path does not fall off after the pitch change. For completeness, we will repeat these corrections from above the glide slope. Notice that the corrections from above the glide slope are essentially equal to corrections from below the glide slope. Because of this, we only need to look at corrections from below the glide slope in the following simulations. Now let's look at the responses in the region of neutral command. First, with no pitch or power changes. Next, the pitch-only response. Now a power-only correction. And finally, pitch and power together. Notice that the pitch-only response ends up parallel to the glide slope, and the power response is slightly faster than the region of normal command. Also note that the fastest response is with pitch and power together. In this region of reverse command simulation, the trend as we move from the region of normal command to the region of neutral command continues. Here is the flight path with no changes in pitch or power. Now a change in pitch only. Now a change in power only. And finally, a change in pitch and power together. In this case, after an initial move toward the glide slope, the pitch-only response then diverges away from the glide slope. Also note that the power-only response is considerably improved relative to the other two regions of command. In addition, the fastest response is again with pitch and power together, and is identical to the other two regions. Now let's compare pitch-only and pitch and power together corrections for all three command regions on the same screen. First, the flight path with no changes in pitch or power. Now, pitch only in the normal command region. Pitch only in the neutral command region. And pitch only in the reverse command region. Now pitch and power together in the normal command region. Pitch and power together in the neutral command region. And pitch and power together in the reverse command region. How do we explain these results? First of all, the initial move toward the glide slope is caused by the exchange of airspeed for altitude. In other words, exchanging kinetic energy for potential energy. However, the flight path direction will continue to change as long as the airspeed is changing, which will continue until the forces parallel to the flight path are balanced. In a descent, drag is balanced by thrust and a forward component of weight. As airspeed is reduced in the normal command region, the reduced drag requires less forward weight, which is obtained by a reduced descent angle. The neutral command region sees little change in drag as airspeed is reduced, so the same forward weight is required to balance the same drag, and the final flight path direction is unchanged. A slower airspeed in the reverse command region produces increased drag, which requires an increased value of forward weight that is obtained by a flight path that is steeper than the original direction. It is now easy to see why the combination of pitch and power together sustains the original direction caused by the pitch change. The change in power prevents any change in airspeed, so the new flight path direction is maintained. We see here that pitch-only corrections are a useful technique only in the region of normal command. We also see that pitch and power together provide the best flight path response in any command region. It also has the advantage that airspeed remains constant while correcting glide slope deviations. Now we will look at power-only corrections for all three command regions. First, no changes in pitch or power. Now power only in the region of normal command. Power only in the region of neutral command. And power only in the region of reverse command. Next, pitch and power together in the region of normal command. Pitch and power together in the region of neutral command. and pitch and power in the region of reverse command. The reason that flight path response to power changes improves as we move from the normal command region to the reverse command region is reasonably straightforward. In the normal command region, drag increases with increasing airspeed, so that the difference between thrust and drag decreases as the speed builds, which reduces the acceleration. Remember that in a power-only correction, the change in lift that causes the flight path direction to change depends on airspeed. In the reverse command region, drag decreases with increasing airspeed, increasing the difference between thrust and drag, which improves acceleration. Since there is little difference between thrust and drag while accelerating in the region of neutral command, acceleration for a given power change is midway between the accelerations of the other two regions. In addition, increases in angle of attack at slower speeds increase the thrust component that is perpendicular to the flight path, so changes in thrust have a direct effect on flight path direction at slow speeds. Note that the fastest response to power-only corrections occurs in the region of reverse command, where pitch-only corrections will not correct for glide slope errors. But as before, pitch corrections combined with power adjustments to maintain a constant airspeed still provide the fastest flight path response in all command regions. Now that we understand pitch and power response in all three command regions, let's take a look at the drag curves for three airplane types. At a typical speed during an ILS approach with competing jet traffic, a light airplane is normally well within the region of normal command. Therefore, pitch-only corrections to maintain the glide slope are very effective, so the easier method of correcting glide slope deviations with pitch and allowing the airspeed to vary is an allowable choice during an ILS approach for light airplanes. Since the final approach speed can be in the region of neutral command, coordinated pitch and power adjustments are required. Jet transport approach speeds are almost always in the region of neutral command, so coordinated pitch and power corrections are required here also. In addition, there is a basic difference in airspeed adjustments in the region of neutral command. In the normal command region, a new power setting delivers a new airspeed, which remains constant. Since airspeeds in the region of neutral command require almost the same thrust setting, speed corrections require a change in thrust, followed by a return to the same thrust setting after the speed deviation has been corrected. Now is a good time to look at the next question on our list. Why are U.S. Navy fighter pilots taught to use a technique that is opposite to that used by U.S. Air Force and airline pilots? Let's look at the drag curve for a typical jet fighter. Typical approach speeds for a jet fighter landing on a runway can be in the region of neutral command, where pitch and power must be used together to provide timely glide slope corrections while maintaining a constant airspeed. Carrier landings require the absolute slowest safe approach speed, which is usually significantly slower than required for runway landings. Therefore, jet fighter carrier approaches usually are in the region of reverse command. Although coordinated pitch and power still provide the quickest flight path response in this situation too, the catastrophic effect of a pilot correcting with pitch only without a power change, plus the increased power only response in the region of reverse command, make a good case for the Navy to teach their pilots to control glide slope with power and angle of attack with pitch. In this case, angle of attack is just another way of measuring airspeed, with the advantage that approach angle of attack does not change with weight, while airspeed does. The Navy technique trades a small amount of precision and flight path control for the protection of pilots who might attempt to control flight path deviations with pitch only. A flight path error using power only can result in a go-around, but an error using pitch only may be the pilot's last carrier approach. This being said, It is not hard to find Navy fighter pilots that will admit to making tiny pitch corrections to snag the correct wire just before touchdown. This simulation shows the control response advantage to using coordinated pitch and power together if you didn't have to worry about someone using pitch only without power. This is the pitch only correction. This is a power only correction. And finally, pitch and power together. We have discussed typical command regions, but there is a simple way to determine what command region a particular airplane is operating in. Let's demonstrate the procedure with computer simulation. To find what region of command you are operating in, simply set up a stable, level flight condition in smooth air at the airspeed and configuration that you are interested in. Then, with no change in power, increase and hold a pitch attitude that results in an airspeed reduction of 8 to 10 knots, and watch the vertical speed indicator. If the aircraft is in the region of normal command, the vertical speed will remain positive after the airspeed stabilizes at its new lower value. In the region of neutral command, the vertical speed will return to a value near zero, and in the region of reverse command, the vertical speed will stabilize at a negative value. In this first example, our simulated jet transport is in the landing configuration, and at 200 knots is in the region of normal command. After the pitch change and the airspeed stabilizes, note that the vertical speed remains positive. Next, we are in the region of neutral command at 130 knots. Note that the final vertical speed is near zero. And finally, at 100 knots, we are in the region of reverse command. As expected, we see that the final vertical speed is negative. The altitude versus distance screen shows the three flight paths. This procedure will identify the command region in any airplane and at any airspeed and configuration. Now let's discuss our last question. The last question is, why are so many light airplane pilots being taught pitch and power control methods that are contrary to professional pilot procedures? There are at least two reasons. The first is related to the traffic pattern from long ago. Fear of engine failure left over from the very early days of aviation, combined with the long glide capability of older general aviation trainers, caused flight instructors to teach the 180-degree accuracy approach as the standard traffic pattern method. Every approach was considered to be practiced for a potential forced landing. This procedure consisted of closing the throttle opposite the point of intended landing, and then adjusting the size and shape of the flight path in order to touch down at the desired spot without adding power. If power needed to be added, the approach was considered a failure, to be corrected on the next approach. Since this is a power-fixed approach, pilots were taught to control airspeed, the only thing that could be measured precisely, with pitch attitude. Since these power-off approaches resulted in relatively short final approach segments, anyone flying a larger pattern to enjoy the advantages of a more stabilized approach interfered with those flying the power-off approach. The angry words directed toward anyone flying a perceived long final approach can still be heard today. In the 1960s, new general aviation trainers had higher wing loading and steeper glide ratios, which required power to be used during descent in the traffic pattern. This, along with increased traffic, resulted in larger patterns which caused the power-off approach to largely disappear. However, the practice of controlling airspeed with pitch attitude remained. Since being a flight instructor is a beginning job in aviation, instructors typically taught what they had been taught. By the time that instructors moved on to the airlines, where throttle controls airspeed when flight path is being controlled by the autopilot or flight director, it was too late for them to go back and change what they had taught their students. The second reason that instructors teach their student pilots to control airspeed with pitch is a safety consideration similar to that used by the Navy for carrier approaches. If student pilots cannot be relied upon to coordinate power changes with pitch changes, and tend to make only one correction for flight path deviations, the safest method is to use power only rather than pitch only. If the flight path is not accurate enough, the student pilot is taught to go around. This technique may be necessary to allow some student pilots to survive their early experiences. The problem is that they are not taught the most responsive method of flight control later in their training when they have the skills to avoid controlling flight path with pitch without an appropriate adjustment in power. Hopefully we can now understand how controlling flight path with power was established in general aviation training and why it has persisted for so long. General aviation pilots that still use this method must realize that they will be forced to change their thinking when they advance in their aviation careers. Now is the time to see how controlling flight path with pitch can save your life in the event of an engine-out forced landing. This procedure allows a precise approach to a landing site after a total engine failure. It uses our natural ability to sense direction combined with the responsive control of pitch and roll. When traveling toward a particular point, all the surrounding images move outward from the point as the picture grows in size. Our eye naturally is drawn to the point that does not move, which is the point that we are moving toward. By utilizing pitch and roll control, we can move this point to the desired landing location. In other words, we can fly a straight line from our current location to any particular point on the ground. The question of whether we can fly safely along this line is determined by airspeed. If the speed drops towards stalling speed while flying this line, there is insufficient energy available and a closer landing site must be selected. If the airspeed stabilizes at the desired approach speed, there may be enough energy to get to the point, but without sufficient energy for any required maneuvering. Again, a closer landing site should be selected. When we have chosen a landing site and are flying directly toward it, with a speed faster than our approach speed, we now have sufficient energy for a safe landing. As we get closer, drag is added to reduce speed. Unlike a normal visual final approach, where we are maintaining a specific flight path angle, typically 3 degrees, this case is a steeper approach flown direct to a point on the ground. Using our natural ability to fly a straight line to a point is much easier than flying a specific angle, which requires experience. However, both situations make use of the responsiveness of pitch control. Let's look at a simulated forced landing approach in action. We are about 7,000 feet above ground level, and the engine has just quit. Pitching up to aim toward an airport straight ahead, we see the airspeed drop significantly, verifying that we must pick a closer landing site. Off to the left, I see what appear to be hangars and possibly a runway. We are turning toward and aiming at the hangars, which appear to be reflecting sunlight straight ahead. Checking the airspeed, it is well above our approach speed of 70 knots, so we know we can safely make it to this point. The engine out checklist has been completed with negative results. As we get closer, we can fine-tune our aiming point. We see that our speed is now too high, so we added 1 notch of flaps. The flight path is progressing nicely toward the runway that we can now clearly see. The speed is still too high, so another notch of flaps is added. Speed is getting a little slow, so 1 notch of flaps will be retracted. We are close enough now so that our flight path control is more precise. Flaps are extended or retracted as necessary to keep the speed slightly above approach speed. Full flaps are added when landing is assured. If we have picked a landing site that is not straight in, we would aim toward the point where the turn to final approach would begin, plus sufficient distance to account for the turn and the final approach segment. Otherwise, the procedure is the same. One final comment. If we can make a precise approach from 7,000 feet, controlling flight path with pitch, we should have no trouble always passing over the end of the runway at the desired height during a normal landing approach using the same technique.